So, meanwhile, do you have any doubt regarding?
Yes, yes. Regarding I wanted to know that in power electronics,
Hmm.
the DQ reference frame and ABC to DQ reference frame and alpha beta. In
Okay.
that, I know regarding this drives one.
Mm-hmm.
When I was doing that drives one, it was
Mm-hmm.
okay.
Mm-hmm.
But in the power electronics, why it is coming that P term in the power electronics term, D by dt term.
Uh, DQ terms.
DQ terms I know, but with the reference,
Uh-huh.
but in the lectures
Mm-hmm.
or somewhere I have seen
Mm-hmm.
why it is having the LDI by we will do that LDI by dt, right? We will
Okay, okay.
P
Let's.
is coming.
Okay, okay.
Uh,
Uh,
why? That
just
is
a
the question.
second. Let me share my screen.
Okay.
Yeah. So, which lecture are you referring to? This one? No, not this.
No, sir. And the modeling,
Modeling.
not modeling, then not in modeling, I think. Uh, I have written so many doubts, but I was not able to find now.
Okay, okay.
Uh,
No issue, no issue, no issue. Just let me. Here we have some DYDD terms. These are from the machine parameters. Uh, like dy/dt of lambda. This is because of the
these
induction
are machine terms only.
machine terms. Yeah, yeah.
Machine terms only.
Drives. Yeah. This is not. It can be. I think. Just a second. These terms.
Yes, sir.
Okay. Mm-hmm. I think I also haven't gone this much, but this is
Not we are in the we are not had two lectures,
yeah,
two
yeah,
last
yeah.
sessions.
Because one lecture I was not feeling well. The last lecture we had
Okay,
a network shutdown in the campus,
okay.
so that's why.
The IT Kanpur.
Yeah, yeah, yeah.
Okay.
So yeah, so these terms are coming because of the fact that the converters, I think these are inverters actually. So you have a DC input and a AC output, I guess. That's why these terms are coming. Also MIQ VDC by 2, these kind of expressions come from inverters only. So I think inverters.
Just why it is coming? Okay, sir. But any
Hmm.
derivations I need to go through because to
Oh yeah,
understand the things.
no, 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 nothing. You can do it by
And
yourself only. So basically, uh, in case of inverter, so right. and oh no, this won't be ground. Okay, so we placed it to ground. Let's connect this to ground as well. So this L, let's see. So the switching here is done, let's say, such a way that one, two, three, four. So 1 and 4 will turn on simultaneously, and when 1 and 4 are off, 3 and 2 will be on. Okay, now what is done is basically triangular, like this. A high frequency triangular wave is generated, right? And the sine
Okay.
waveform is compared with this triangular wave. So when you compare that, you will get a PWM signal.
Okay.
Like this, pardon my drawing. So
Yeah, I understood.
so this type you will get some PWM signals, and when it is high, 1 and 4 is on. When it's 0, 3 and 2 are on, right?
Okay. Okay.
So accordingly, if you do that, if the peak of the sine wave is, let's say, m, where m is the modulation index.
Sir, can it be modulation index? Can it be greater than 1?
No, no, it cannot be greater than 1. It's maximum 1.
And then it will be switching will be not be done, right?
Yeah, yeah. Greater than 1 means what? That the sinusoid will go
R-
past the triangle's peak. So
yes, yes.
it's basically will lead to over modulation, means there will be distorted waveform.
Will it be switches will be on at the time?
uh, since the sine is above, no, switches will be off, right?
Oh.
Because uh, the
Then how it will be that there will not be any output, right? Outside or output.
just a second, when the sine is compared, so just a second, sine is triangle. So when sine is greater than the triangle, oh, okay, sorry, when sine is greater than the triangle, then there will be PWM. So if it goes past, yeah, it will be on at that time, because
Sir, can you tell me with the reference to the reference and carrier waveform, which one will be the carrier is a sine wave, right?
this is the carrier, triangle,
The sine wave, triangle. Okay,
triangle waveform.
triangle is a carrier. Then okay, okay.
This is the high frequency one, usually at 10 kilohertz or 20 kilohertz, and this is 50 hertz component sine.
Okay,
So this is your modulation input.
okay,
So comparing them, where sine goes to the positive of the comparator, triangle goes to the negative of the comparator, you get the PWM signals.
okay.
Now if you do the calculation, so you will end up with the sinusoidal voltage at the output of the inverter at this point. Let's say this is VC. VC will be something of the form m by 2 VDC sine of omega s, omega not omega s, sine of omega t.
VC equal to
VDC.
voltage across capacitor equal to m by 2.
M by 2 VDC sine omega t. M is the
Okay.
modulation index, VDC is the input DC voltage.
Okay. For the full half wave one m by 2, right, sir? For the full wave one, it is m, right? M sin VDC by omega t.
Yeah, for there are two ways you can give the get pulses. So one is the bipolar,
Okay.
another is unipolar. So I don't remember exactly, but for one case it is m by
Okay.
m VDC by 2, and for the other case it's m VDC.
Okay.
So it's, in case of bipolar, this is what I explained. In case of bipolar, that 1 and 4 will always operate and 3 and 2 will operate. In case of
Okay.
unipolar, this is not the case. In case of unipolar, when for the positive half, uh, means there will be 1, 2, 3 and 4 will switch independently depending on the PWM. So there is no uh, like constraint. Here there is a constraint. When 1 will turn on, 4 will also turn on. In case of unipolar, there
Okay.
is only one constraint, that two switches of the same leg cannot turn on simultaneously. They will turn on complementary manner.
Okay. Okay. We'll carry on with the what we discussed.
So yeah, so that is the case. Uh, Detailed derivation I also don't remember exactly, because I don't work in this, so that you need to check out.
Okay. But
But I can give you references if you
is
want.
there any reference? Yes. I was asking that one.
So you can go through, uh, there is a book known as Iravani. So you can follow his book on inverters, voltage source inverters. So there you can get how you can also do it by your own also, because you have to apply the same concepts that you have learned for DC to DC converter, uh, like flux balance condition, charge balance condition. Those will also be valid, because the output sinusoid is of 50 hertz, whereas the switching is happening at 10 kilohertz, 20 kilohertz range. So you can also apply.
What the LDI by dt
Hmm.
is the it is the outside of the circuit, not the with the inverter.
uh,
And it is omega also is there, and
Omega will be there because they are converting it to DQ frame, right? So in DQ, when you are referring it to the
yes.
rotating axis,
Mm,
so the di by dt's will be changed to omega, because
okay.
so dq by so basically it's what, so the voltage that you are getting at the output of the inverter, they consider it to be the d axis, analogous to what we have learnt in drives. Okay, in drives what we do, the
Okay.
in the voltage that we apply to the motor will generate the flux, Sorry, in the rotor,
flux.
the flux direction we
We,
consider it to be the d-axis, and the axis that is quadrature to it, we call it to be q-axis.
mm,
Right, so here we don't have any flux, so what we do here is d-axis will be uh, the phasor in phase with the uh, inverter output voltage, that is d-axis, and a quadrature to it, it will be q-axis. Now it is a rotating frame at 2 pi into 50 hertz radian per second, it's rotating. So basically what you will obtain is DC values, right?
yeah.
So whenever you have L di by dt, so if I has some component, so it, say I is your some I sine omega t plus phi, so di by dt will give you omega I with a minus cos of omega t, not minus, yeah, cos of omega t plus phi. So what you obtain here is L omega I cos of omega t plus phi. Now if you divide it, so you will get L omega I cos phi cos of omega t plus minus L omega I sin phi sine of omega t. So let's say uh,
Okay.
we have d-axis is sine omega t, so your id will be minus L omega I sin phi, and iq will be L omega
And
I
another.
cos phi.
Okay.
So omega term is coming out, right?
Okay.
Just a second.
Sir, and
Huh. Yeah, go ahead.
sir, in the lecture
Hmm.
of the eighth lecture or something, there is
Okay.
kind of measuring means
Eighth lecture.
which eighth or ninth something.
Ninth. Ninth
This
I have. Yeah. Yeah. So this is the bipolar. Okay.
mm,
This is bipolar modulation. This is unipolar.
some multi-level convert. Sir, this
Hmm.
full of converters is very doubtful, sir. In this
Yeah.
cascaded one, bidirectional DC converter, mm,
Bidirectional DC.
H
This is these are all
H bridge H bridge.
these are all DC to AC. So I think it's 10. Uh,
Okay, these are at the second lecture only. I haven't. I have.
no, this is. These are the three phase. Mhm, this is also not. Ah, here DC to DC. Here, this one.
This one, sir.
Yeah, go ahead. What is the issue?
Operation is I am not able to understand, sir.
Oh,
Uh,
operation. Okay.
that is thing.
Yeah.
Mm.
So Acha, can we draw it on Adobe also? Pen. Yeah. So okay, let's make it here. So so let's concentrate on the primary side. Okay. So
Okay.
primary side we have a DC voltage. Okay. Now this H bridge will operate as a normal inverter having a 50 duty ratio, like 50% of the switching
50%.
period S1 and S4 will be on, 50% of the switching period S2 and S3 will be on, right? So how will be the
Okay.
waveform?
Square, quasi square.
What is happening? Oh, let me draw it in the board as well. Okay. So let's first draw V1. By V1 I mean, where did it go? Huh. This voltage VH1. Let's draw VH1 first. VH1, it's like this. Okay, so this is VDC, this is minus VDC. Now next we have the secondary bridge. So here also we have a voltage stiff C2. If there is load, it's voltage stiff, so we can consider that here also we have a DC voltage at the output, let's say. Yeah.
Yes, sir.
Okay, so the same thing we can draw at the input of the bridge H2, but the catch is we will provide a phase shift.
We just provide the thing. Yeah.
So this is V out minus V out, so this is the phase shift given phi. Okay, so now what you essentially have, let's remove the transformer. So transformer, just uh, the n is to 1 transformer is there. Just for simplicity, let's remove the transformer. So we have just a inductor, right?
Yes.
So this is VH1, this is VH2. Now if you see uh, the voltage across the inductor, the voltage that is being applied is VH1 minus VH2,
VH2.
which is a periodic waveform,
Yes.
right? So accordingly the current will flow through the inductor. So this is a,
Sometimes charging and discharging.
yeah, this is a periodic waveform with the same switching frequency as these two. So this is the uh, period, so, what should I say, time period of the current
Time period
waveform.
will be time period will be different, right, sir?
No, same, because this is also switching at
Sir, because
omega is.
if it is shift, if it
Mhm.
No, it is just
Phase shift is being done.
with
Frequency
VDC.
are same.
Oh, okay.
Because if you
Because VH1 minus VH2,
huh.
then not it will be done. While subtracting, I am asking, but
Just subtracting,
uh,
yeah.
uh, at
Okay.
the
Yeah, go ahead.
hello.
Yeah, go ahead. Hello.
But hello,
Hmm.
hello.
Yeah, go ahead.
If it is phase shift, if it is shift, will it be the same frequency? I'm asking, sir.
Yeah, because if you're giving a suppose if there is sinusoid instead of a square wave and you give a phase shift, it will be the same, it will have the same frequency, right? If the previous one was sine omega t, this one will be sine omega t plus 5. So how come you have your frequency remains the same, right?
No, sir. I am asking that if it is phase shifted by if sine is phase shifted into 90, some of the shifted,
Hmm.
like cos, it become cos.
Yeah.
If it is they are being subtracted, some
Hmm.
other wave will come, right? I am asking that.
No. When
Other.
how can that happen? Because uh, when you are subtracting sine omega t minus cos omega t, it's a linear combination of the same sinusoid, right? So
Yes, yes.
when you do Fourier analysis, so you get a sine term plus cosine term. So combining them, you can write a sine of omega t plus phi, where phi equals to tan inverse this cos coefficient, sine coefficient minus cos coefficient. So the frequency
Okay,
remains
okay.
the same. Frequency doesn't change with the phase shift. So the current, this current will also have the same frequency omega is, it will be a periodic current. Now
Okay.
so this is how you will get the current. Now to get the output voltage, now the output voltage is basically like this. So there is a capacitor, and if there is a load, there is a resistance R. So this is the current IL into the sine of VH2. So when VH2 is negative, minus 1 will be multiplied to IL. When VH2 is this VH2 positive, plus 1 will be multiplied.
Sir, can you explain me after this one? VH1 minus VH2.
Okay, so you get the current, right? IL here.
Where, sir? Just to point
L,
it with the cursor.
so VH1
Okay.
minus VH2.
Okay.
So there will be a current IL that will be flowing. Now,
Okay.
okay, let me clear it in a different way. Um, Now let's concentrate at the output side. So this portion. So what will be the current? So whenever Q1 and Q4 are on, V plus V2 will appear across VH2.
Yes, sir.
Whenever Q3 and Q2 are on, minus V2 will appear across VH2.
Yes.
Whenever Q1 and Q4 are on, if this is IL current only will appear on this side. See,
Nice.
yeah.
From
whenever
but the direction will be different, right?
no, direction will be same. Q1 and Q4 are on. See,
Q1.
this will be the direction, right?
Mm, yes.
But whenever Q3 and Q2 are on, so direction will be like this. So basically this is the direction of current, so it will go like this. So the current direction has changed.
Okay.
So that's what I am saying is so we have two intervals. When Q1 and Q4 are on, then we need to consider the positive current, that is the current that we have, and when Q3 and Q2 are on, we have to consider the negative current. That will give us the DC, and then we have to remove we have to take an average of this current over the duration Ts. Then we will get the output current, or the current that is flowing towards V2.
Means where the load is connected, sir. Means
In
how
place of V2,
if the
I
sub.
am saying that V2 is not there, there is a load then, or
Uh,
also if there is V2 also, if whatever current is here, it may not be a load. If the power may flow from the secondary to primary side, whatever current is
okay.
flowing here, that will be basically the average. So it will be like this. So I naught will be equals to 1 by Ts integral 0 to Ts I 2 dt. This you
Okay.
can this is perfect when where this is
Yes.
I2 and this is I naught. So the average current will flow through uh,
Resistance and
the ripple will flow through the capacitor. The average portion
capacitor.
will go to the
Mm,
that side, load
resistor.
or whatever
Okay.
is there.
Load. Mm.
So now I2 can be written as 1 by Ts integral 0 to some phi, it is minus V naught, so it will be minus IL dt plus 1 by Ts phi to not Ts, I should be writing okay, this will be since this is sim what should I say, half wave symmetric, so we can consider it over Ts by 2. So 0 to pi
Mm.
and phi to Ts by 2. This portion, the current is same as the inductor current, so it will be
Next
IL
half.
dt. So from here you can get the I naught.
Sir, can you slide in which lecture, sir?
Mm-hmm.
Where
Acha,
show me the lecture slides.
in lecture,
Next one.
yeah,
Mm, this one.
okay. So yeah, this is the inductor current, as you can see, the blue one.
Mm.
Okay, so these
Okay.
are the this is the VH1 50% duty. This is the VH2 also 50% on, 50% means 50% Q1 and Q2 are operating 50% of the time, Q2 and Q3 are operating. So but there is a phase shift. This is the phase shift, this is the phase shift phi. So this gives you the inductor current like this. So as you can see, from this point to this point, whatever is the waveform, from this point to this point, we have the same waveform but inverted. So
The
this is
same.
half wave symmetric. So that's why I'm saying that analysis for Ts by 2 duration is sufficient to, because it's essentially twice. If you take an average over TS, if you take an average over TS by 2 and double it, not double it, sorry, the average across TS by 2 is same as the average over the whole TS duration
into 2
mod.
Okay.
Yeah,
Okay.
so that's what I'm saying. So yeah,
So
so
next slide.
huh so yeah, from here the average power transfer also can be obtained. So um, yeah, this, what is THS? Sorry, THS is the half time, means TS by 2 it is. So this can also be this can be computed. So you want me to derive this?
Yes, sir. How the power can be uh,
uh,
derived.
okay, this expression, right?
Expression.
Okay, let's do it then. Okay, so we have this. Okay, okay, let's do it together. So what we have, essentially we will be requiring to do the analysis for TS by 2 duration, because the rest will be the same. So in this
Okay.
duration what we have is, so V1 minus of minus V2, so V1 plus V2, and then we,
The 0.
no, not 0, this duration we
V1.
will have V1 minus V2.
Okay. Okay. V1 minus V2. Oh, the voltages may not be the same. Right?
Yeah, okay, V1 plus V2, V1 minus V2.
It,
Okay, fine. uh, okay, okay, so next what can be done, just let me go through. Okay, so this is my TS by 2 duration. So L di by dt equals to V1 plus V2 for 5. Let's Acha, what is being declared as D? Let me just check. D is, acha, the phase shift is considered to be dTs by 2. Okay, so this phi is considered to be dTs by 2. Okay, so it's into dTs by 2 plus V1 minus V2, 1 minus d Ts by 2. So we have L, um, okay, so mhm, hmm, so from here I can say, let's say we have current at this point is IL1, let me use a different ink. At this point we have IL2, and this point we will have exactly minus IL1. Okay. IL1, IL2 and minus IL1. So we can say one thing for sure, that L IL2 minus IL1 by dTs by 2 is equal to V1 plus V2 and L this would be minus IL1 minus IL2 by 1 minus dTs by 2. This is equals to V1 minus V2. So we have these two expressions. Okay. Okay. So how can we go about this? Can be done. Just let me. This portion is obtained, so we obtain basically 2 IL1 and IL2 in terms of V1 and V2 I can obtain. So I need to obtain the power flow. Okay. One thing can be done is power out is equals to V2 into I2. Now what is I2? I2 equals to 1 by Ts integral 0 to phi, it's minus IL dt, that's 1 by into ts by 2 il dt. So it's basically the this portion we will have minus 2 by ts il1 plus il2 into this duration, that is dts by 2. So 2 cancels out, ts cancels out, plus 2 by ts. What we have here is okay, so okay. So to find out this area, we have to find out the area of this triangle minus the area of this rectangle, right? So the area of the triangle will be il1 plus il2 into 1 minus d ts by 2 minus 2 by ts. The area of the square is il1 into okay, there will be a half, so 2 cancels out, half into height into base, so hence we can obtain minus d il1 plus il2, okay, plus ts cancels out, 1 minus d by 2 il1 plus il2 minus 2 no 2 ts cancels out again, so we are left with 1 minus d il1. Is it okay till now?
Okay, sir.
Okay, so minus 2d, this will be il1 plus il2, this will go as plus il2 1 minus d 1 minus 3d by 2 minus 1 minus d il1 so this is equals to il1 1 minus 3d minus 2 minus 2d by 2 plus so this is plus il2 1 minus 3d by 2, so this comes out to be il1 minus minus IL1 1 plus d by 2 plus IL2 1 minus 3d by 2. Okay, so basically the power flow will be equal to V2 into I2, which is this expression. So we have now we need to just find out IL1 and IL2, right?
Yes.
Any doubt till now?
No doubt, but with integration of IL is why it is coming as IL1 plus IL2. 0
Integration
to
of
5.
this, right?
0 to
0 to 5.
0 to 5.
Yeah, so see 0
That
to
is
5 this
IL.
duration. So this is the area, right? This is the
Okay.
this
Trapezoid one. Okay.
trapezoid. So area of trapezoid.
Okay.
And here we have done is area of rectangle, triangle minus the area of this bottom rectangle. So yeah, okay.
Okay.
Yeah, so yeah, from here we can find out v1 plus v2 into dTs by 2 L is your IL2 minus IL1, and here we have v2 minus v1. Let's say d prime to 1 minus d. Ts by 2 L equals to IL1 plus IL2. So this gives us twice IL2 is equal to the addition of these two. So the IL2 will be half of V1 plus V2. Oh no, the addition of the two, right? Yeah, d ts by 2l plus d prime ts by 2l, and I'll1 is half v2 minus v1 d prime ts by 2l minus v1 plus v2 d ts by 2l. Okay. Now substituting these to the above expression, what we can have is P V2 minus no B2 into I2 can be written as IL2 is this, so it's basically half into 1 minus 3 d by 2 uh, divide 2 v1 plus v2 d. Okay, let's take the 2 by L term outside. So 2 by L is here. So d plus v2 minus v1 d dash plus, not plus, it will be minus.
Sir, I will check it once again, sir, because some
Yeah,
calculations I will go through that, and
you can
if
go
it
through
was
calculations,
not
right?
coming, then
Yeah, so basically you
okay.
understood
Yes,
the way it should be done.
yes.
So if you simplify it, I think you will get that only,
Okay.
that expression. Yeah, so any more, so yeah, from there you will get, and from, if you get this expression, so by varying the duty d, you can easily confirm that it will be d minus d square. So if you take a derivative, it will be 1 minus 2d. So d equals to half, you will get the maximum power transfer. So it's half into half, that's 1 by 4, this expression. Yeah,
Okay.
so this also can be obtained easily. Yeah, and this is the boost converter modeling. uh, what I have done is the
These are fine. Okay.
this portion, if you're not familiar, if anyone is not familiar, so there is a video also uploaded in the link, doubt clearing session, so that covers the entire discussion of how to model a boost converter, both for steady state analysis and dynamic analysis.
Sir, can you tell me these concepts, voltage control and current control, inner loop and outer loop one?
In a boost converter,
In a boost converter or any converter in
yeah,
the with the
so
solar in
yeah,
one.
so the basic
Yes.
difference is as follows. uh, in case of voltage control, what we do is we measure the output voltage, compare it with a reference voltage, and pass it through a controller to generate a duty ratio which will operate this
Mm.
switch, and thus the control is done. Clear?
Okay.
For voltage control. In case of current
Mm.
control, what is done,
Mm.
again the output voltage is measured. So
Mm.
we measured this voltage. After measuring this, we compare it with a reference,
Mm.
and we generate a through controller, we generate a I reference.
Okay.
Okay, now this I reference is compared with the current that is measured at the inductor IL. These two are compared, and then there is a is it here, there is a standard way of yeah, so this is the voltage control, this is the current control. So current, this inductor current is being measured, and the uh, I reference is being provided. So then it is passed through a comparator stage. So that comparator stage basically involve, after comparison there is a SR flip-flop stage which provides the required duty PWM to the switches.
Yes, sir. Flip flop.
Hmm? Yeah, SR
Sir,
flip-flop, SR latch. Yeah, SR latch.
why sir? Let's sir. Why?
Okay.
Set and reset one only 0 1 and 0 point.
Yeah, so SR,
With that
why
one.
we use SR latch? So this portion of the control is very simple. So this is how it's done. So you have a comparator, right? So plus minus. So you have this IL, this is the IL, and this is I ref, right? and this portion will directly go to the R, and in the S we will have the won't be having the clock. What we will be having is a edge triggered operation, like at every positive edge the S will be given a 1.
Okay.
Okay, at every positive edge. So what happens is, so your inductor current, so this is your I reference, suppose this is your I reference, your inductor current is increasing. The moment it goes above, what happens is IL goes greater than I ref, R becomes 1. As R becomes 1, Q becomes
Yes.
0.
0.
So Q becomes 0. Again, after the start of the clock pulse, it goes high. Again, when it crosses, it goes 0. So the PWM is thus generated.
Yeah.
Okay.
Sir, where I can find these concepts related
Okay.
to with the saturation
Yeah, yeah.
blocks?
So the book name is Fundamentals of Power Electronics by Professor Robert Erickson.
Okay. Okay.
So there you can find this. So
With the
this is known as,
about the blocks,
yeah,
all
there
the things.
everything is there. So this is known as current program control. There is a complete chapter on current program control.
There are two three methods: the peak control and average
Average
control,
control, everything is
and
there. Yeah, yeah. The peak power control is known as the current program control.
okay. Sir, why is there any instantaneous response will be from the uh, in the eighth chapter, some kind of thing,
Mm-hmm.
eighth or seventh?
Mm-hmm.
The sir told that it is a fast response, dynamic response. Current has a fast response. That's why we are using this one current control.
Yeah.
Uh,
Acha,
some kind of is there?
why current is a faster response and voltage is
Yes,
a slower
yes, yes.
response? That you are asking.
Yes, sir.
So
Yes.
basically, means it is not that um, the current response is a faster one, but the if you just um, write the transfer function considering the current loop only, and
Mm.
then you will get certain time constant, the certain crossover frequency,
Yes.
right?
Mm.
Just ensure that the crossover frequency of
Oh,
the
by the
outer loop is
by
1/10 of that.
okay.
Then only the
Okay.
very assumption that you are taking will be validated,
Okay.
because if its crossover frequency is 1/10, meaning that its its settling time will be 10 times more, so it eventually becomes a slower
Okay.
process, the outer loop.
Sir, I'm asking in every not in the power, not only in the power electronics,
Mm-hmm.
in the control systems,
Mm-hmm.
blocks will be there, right? Saturation block, a PI controller. With the PI
Saturation block
controller,
is
which
not
which
needed.
one we
Saturation block is inherent. Like if you use an op amp
inherent?
circuit, it's
Mm.
saturated till the real voltages, right? So it's inherent.
Yes, yes. Mm. Means saturation block means what it will give if you put the saturation block, the voltages get saturated and the output will be given as that's it. what we give.
Yeah, voltage will be saturated at that point.
Okay.
So
And
that is
if
not
PA controller,
yeah, yeah, go ahead.
if for PA controller various inputs will be given and various outputs will for if we give the voltage then it comes current, and if you give the power Q P
Hmm.
reactive real power,
Hmm.
some other form will it come, like in the blocks I am asking,
Okay,
how we that's that concepts where I can find, and
please
could you
repeat.
tell me
I
that?
didn't get actually.
Hello.
Yeah, go ahead.
Where I can find regarding the
Huh.
hello,
Yeah, yeah.
where I can find the detailed information about the blocks which are used in the MATLAB regarding the feedback loops and the PA controller, which one is given as input and the output will be current, like that it will become right.
No, yeah, actually you need to design.
Design, I'm asking how it will design means if only the 1 by kp and ki by
KI
s
you need
it
to
will
design.
come, right, sir? Only the we will design only the constants value, right?
Yeah,
Tuning will be there.
yeah, tuning of the controller.
Uh, only tuning will be there, but I'm asking that which inputs will give the output, which output will it will give, that type of information I ask.
Oh, okay.
If I given the current as an input,
Acha, you
what
want
it will come as
reference?
the output, if
You will find it in
uh,
Ericsson only.
okay.
Yeah.
Okay, sir.
Okay. So yeah, yeah. So DC-DC converter is this much only. So yeah, you can go through that video also that I have shared. That covers everything, that how to achieve steady state analysis and dynamic analysis in boost converter. So any more query regarding DC to DC converters? And this one you can I have shown you how to
No,
do
sir.
it, so you can just do the calculations, right?
Yes.
So
Yes, sir. Yes,
yeah,
sir.
so
Really.
tomorrow can you let me know that whether it's you're getting the same expression or not?
Okay. Okay. Okay.
Okay. So yeah, and rest what we have this is rectifier circuit. So rectifier stage, uh, PWM rectifier stage, yeah. So here what we are doing is basically controlling the switches so as to obtain a desired output voltage as well as a unity power factor at the input. So uh,
In the multi-level
hmm,
the switches will be series.
switches will be
Switches means the sources are in series,
hmm.
or what kind of how it will be done.
In multi-level converter what is done is there is a there is no single switch, there is a switch module for every in every leg.
Oh,
So each module consists of, let's say, six
okay.
seven switches. So that way it is done. So the control becomes more
Means
complicated. Mm-hmm.
if a full bridge inverter is
Hmm.
from full bridge inverter we can get a square wave which is having 50% cycle, like that.
Huh.
uh, like that there are kind of four switches in that one.
Four
In
switches.
multi-level
In
converter, how
multi-level,
many switches?
there are multiple switches. Like you have to first design the control strategy or the modulation strategy in which way the switches will operate in order to get that staircase like waveform. Like it will rise small
Oh, yes, yes.
staircases
Mm.
till the top, then it will slowly reduce. So to achieve that, what will be the switching strategy you need to obtain, and then from there you can know the arrangement of the switches. and their switching. It can be derived from there.
If
Like
hello.
when S1 will be turned on, when S2 will be turned on. So basically what is done is it's done in the level of modules. So suppose there are 4 modules, so this module will operate at this duration,
Uh,
this module. Yeah, go ahead.
with with an example I need, sir, because
Okay.
just in the slide also it is not given in the not proper way.
Okay.
Only the whole waveform is given.
Actually,
The ripple content will be reduced like that.
hmm actually I too don't have an example, but I can uh,
Okay.
share with you it's like the idea what how it is done. So in case of normal
Okay.
inverter, we have 4 switches. Here we have 4 modules, let's suppose. Okay. So we have 4 modules. So we know that this module and this module, suppose this module is M1, this is M2, this is
Mm.
M3, and this is M4. M1 and M4 will operate simultaneously, and M1 and M2 will operate simultaneously, and M3 and M4 will operate simultaneously. So basically, now inside M1 there will be a different there will be the switches, and you will have to operate the switches. Like,
Okay.
so first you decide what will be the switching of each module, then you decide how each modules will be switched among each other. So there's
Okay. Okay.
level by level.
With a mutual understanding of the switches together each other
E-
and individual also.
exactly. So if you do it stage by stage, like first decide how the switches will be operated inside a module. So once that is done,
Okay.
how you have to see how the modules will interact, like when these 2 modules will turn on, when these 2 modules will turn on. And then again, if those modules cluster together to form a bigger module, those modules how they will react. So thus the level by level it is designed. So then what will be the
Okay.
strategy?
Sir, what you said that module consists of source and switches, or the
Only
only
switches, switches,
switches,
only
the
switches.
source
No,
only
no,
switch.
no, not source. Source is
Okay.
different. Now, the source is connected to legs. Each leg has modules. Now, each module has
Okay.
arrangement of switches.
Okay.
So that way it is done.
Okay.
Okay, so yeah, um,
Mm.
yeah. Any more doubt? If I can clarify,
Mm.
um, these are
Mm.
pretty standard. Like, how do you model
I
the
I
induction
I
motor?
I know.
Yeah, yeah.
Mm.
So accordingly you
Mm.
go through it, and there how you will do MPPT. Same goes with the solar also. So you
Mm.
first model the solar cell.
Sir, if means MPPT, if one solar panel is connected to the inverter with the switches, we will play with the switches. Then according to we will get the output voltage maximum and output current maximum. Uh, output power. Eh, Okay. 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 Sir, why the only the boost converter is used as a for the solar or some kind of applications? because there are many DC to DC converters, means buck converter and buck boost converter also is there. Uh, is there any, it we don't use, but buck boost also is there. Is there any special things, advantages kind of thing for the boost? Yes, yes. Mm. Okay. Within the irradiance. Okay. Okay, so say tomorrow same 3 o'clock, right? Okay. Okay. Regarding that one. Okay. Okay. I will tell you, sir, because I have written somewhere, but I am not able to find now. Mm. Okay. Okay. Okay, sir. Thank you. Thank you.